Hello everyone. Today I will discuss a new topic called PID Controller. It is a very important topic in control systems. As usual, we will start our lecture by a quote of the day. Today quote of the day is from Elon Musk, a famous personality of this era. He said, when something is important enough, you do it, even if the odds are not in your favor. So, of course, you should pursue your own dreams and try to be excel in that particular field. So, with this motivation, we will start our lecture today. I divide my PID controller lectures into three major parts. In part 1 and 2, I will cover the theory of the PID controller, whereas in part 3, I will solve some problems related to PID controller. Please recall, we have already studied time response analysis, so we know how to calculate transient specifications like maximum overshoot, settling time, rise time, etc. And we know how to calculate steady state error and what is the meaning of steady state error. So with this note, we will start. So consider this figure first. I believe it is very much familiar to you. It is the block diagram of a closed loop control system where RS and CS are input and output signal in Laplace domain respectively. ES is denoting the error signal. It is obvious that the output CS depends on system and input RS, right? Now, in general, in industry, we cannot alter the system. That means GS and HS are fixed. So if we always try to bombard this system with the same input RS, we will get always same output CS, right? But what if my output is not desirable? That means user wants something else. Okay, so is there any way to change our output or modify our output without changing the RS and the system? The answer is probably no. But we can do a thing. We can employ a third party or we can employ a system called controller, which basically we will try to put inside this system so that by using that controller we can change the output of the system. So our basic objective is to automate the control system. That means maintaining the output within desirable limits by selecting that particular control actions. Now control actions means that third party device, we need to fine tune it to get the desirable output. Now try to grab the concept of controller using this simple illustration. This is a liquid level control system example. So here our objective is to mm, I mean maintain the water level at a particular height h. Now for that we have a tank and there are two taps. Tap number 1 are called inlet tap and tap number 2, let's say outlet tap. Okay. Now using these two taps we need to control the water level. So for that to make it automatically instead of manually, we must employ a closed loop like this one. So here we have first use a sensor, that means basically ultrasonic level sensors maybe and maybe there, and this ultrasonic level sensor detects the present water level and it sends this signal to a comparator, and comparator then compares these two signal. One is reference signal, that means what is desired signal, okay, and with the actual signal, and then produce one error signal if there is at all any error is present or not. If there is no error present, that means the water actual level is at the reference level, then nothing to do. Controller will say that, okay, keep idle. Otherwise, if there is some error, either positive or negative, positive in the sense if the water level goes below the reference level, then you can term this as positive error, or if the water level above the reference level, then you can say that it is a negative error. Okay, so once you get the positive error, that means controller will tell that, okay, I am getting positive error, so that means please turn on the tap 1, so that water goes into the tank, and gradually the water level will be reaching at the desired reference level, right? And if the vice versa, that means if there is the overflow is there, tank is overflowing, so that means controller will say, I am receiving negative error over here, so please uh, switch on the outlet tank and switch off the pump. Okay, so in this way the water level system actually works. So our basic objective here to uh, minimize the error using by employing a automatic controller. Now this kind of thing, schematically we can also draw like this diagram. Here again I want to point out that the controller position is in between comparator, that means error signal, and the process. Okay, so this controller basically connected with a feedback, final control element, which is nothing but actuator. So that's why in my slide, this control signal is denoted by AT, since it is directly connected to a actuator. Okay, and the input of this controller is error signal. Okay, so this is how controller actually works. Now, there are different controllers available in market. So, major controllers are on-off controller, PID, fuzzy, adaptive, robust, and model predictive controllers. These are some, not exhaustive list, of course, but these are the major controllers available. Now, in your syllabus, we will talk about only on-off controller and PID controllers. Okay, so for understanding on-off controller, again consider the old previous example of liquid level control system. Here you must know that there is one constraint. The constraint is the tap 1 and tap 2, they are operating at either 100% on or 100% off mode. That means there is no in between points, like it is not possible to turn on the tap 1 50% or by 25%, not like that. Either the tap is fully open or it is fully closed. So this kind of control action is called on-off controller. So that means depending on this error, depending on the error, actuator will be either 1 or 0. Okay, that means on or off. This can be mathematically represented as by like this. So actuator signal is either 1 or 0 depending on the error, whether it is greater than set point or less than set point. If it cross the set point, then maybe if the cross the set point means, let's say error is positive, that means water level goes below the thing. If it is greater than set point, that means you please turn on this tap. Okay, and if it is below the set point, that means then you please, 0 means turn on this tap. Okay, so here this kind of equation will help us to understand. Now, this equation can also be realized using in Laplace domain like this one, where AT becomes AS, and this is basically error signal ES. But if you think minutely, you will understand definitely that it is not possible exactly to settle down the water level at particular same reference level. Why? Because due to some transportation lag and the actuator function. what I want to say, please try to understand. My question is, I suppose this is my desired water level tank, this red color. Okay. So now, is it possible to stop the water level exactly at that particular thing? Probably not. You can see this diagram. So when the liquid level rises, then error is going to minimize, and when it touch the set point or reference point, then it it will take some milliseconds to give the controller signal that okay, switch off the pump now, or turn off this, cut off this QI, I mean inlet tap. Okay, so but within these 2 millisecond or something like that, or due to some inertia, some amount of water is again pouring into the tank, which will eventually cause some accumulation of water, which cause this kind of overshoot. Okay, once this overshoot is detected by this sensor, again the controller says okay, now over tank is overflowing, so you please turn on this tap. And when it turn on, then gradually it will reduce the water level, and again the same thing will happen. Due to transportation lag, some amount of error will be, constantly we will be getting, right? So this is a very important concept. So the for on off controller, although the construction is very simple and it is a stable solution, but the con is output is oscillatory, and due to this oscillatory output, we never get the error is equal to 0. We will get error tends to 0, but not always exactly to 0. To overcome that oscillatory nature of the output, we can use this proportional controller instead of on-off controller. What is proportional controller? In case of proportional controller, the actuating signal AT is now directly proportional to the error signal. So mathematically, we can write it as like this one. Okay, so please understand the difference. In case of on-off controller, AT must be equal to either 1 or 0. But here, fully on or fully off. But here, depending on the error nature, we can turn on the tap full, not fully, maybe slightly on is also possible here. That means error is, let's say, very less. Okay, so that means your tap should be on, let's say 5%. If the error is very high, that means huge gap between reference level and the actual level, that means your actuator signal will be behave like 1, that means 100% on, like this. Okay, so this is the meaning of this proportional controller. So from equation number 1, we can easily get the equation number 2 by introducing a proportional controller. Now, once we get this proportional controller, we can take the Laplace transformation and we can write down the equation number 3. This equation number 3 can be realized very easily like this one, where ES is multiplied with KP, and then it will give you the output signal, actuating signal AS. Okay. Now, in our class, we have seen that suppose if I give a step input like this one, step input with unit step input 1, and if I take a system like, or normal system like 1 by s plus 2 or 1 by s plus 1, this kind of thing, then, and if you subject to the, just see the output response, then it looks like this one. Since it is a first order system I am talking about, okay, 1 by s plus 2, let's say. So this will be the output. Right. Now the output value is 0.5. How to increase this output 0.5 output? Because I don't want 0.5 output. I want 1, nearly about to 1. So for that, if we increase the value of Kp, we can see a drastically improvement in this, final value. So that means it is try to reaching out the 1 value. Okay. So if we use Kp equal to 1, then this blue line will occur. But if we increase kp equal to 5, then some oscillations are there. That means it is like a second order system. It acts like a second order system. Okay, but ultimately error is also very minimized. Here the error is very high, but in case of red one, error is minimized. Similarly, if you increase further kp equal to 10, then more oscillations occurred, but the error is also less. So you need to smartly choose the value of kp so that the error and oscillations can be managed simultaneously. Okay. Now there are, let us look at these pros and cons. So in case of proportional controller, the pros is it reduces the oscillations, because as you can see at the steady state error, there is not at all any oscillations, I mean, is observed, right? Similarly, it is having good stability, whereas there are certain cons also. The con is if you increase the kp for, I mean, very high value, if you set kp very high value, then oscillations occur. That is a disturbing point. Similarly, it reduces the error, of course, but it is not reduce the error to exactly to zero. But we need sometimes steady state error to be zero, exactly zero, which is not possible with proportional controller.